So, hi everybody, I'm Luca Ceresoli, and I'm an embedded Linux engineer, so my job is to put Linux on embedded devices, on devices with a custom electronics, and I do all the kernel adaptations and so on. I also give a few contributions to the Build project and a few other ones. So I will talk today about some experiences I've had with system on chips which have bad support. There are some with good support, some with bad support. So I will talk about one that I met in the other category. Basically, at least for this talk, I will refer to an embedded system as a physical product that has an electronic board that is designed specifically for that product, a custom board, with a system on chip at its heart. So does anybody don't understand what the system on chip is, or anybody has said so far? Okay, nobody, so you're in the right room, cool. Okay, the chip that I will be talking about is this one. It's from a Chinese brand called Nuvoton, and it's basically designed to allow producing very low-cost devices. Its core is an ARM9 clocking 240 megahertz, so it's pretty slow compared to other system on chip that are very common nowadays, but it has quite reasonable amount of peripherals, many actually, especially an H.264 encoder and decoder, and many others. It has a very peculiar design choice, so it has 64 megabytes of DDR2 RAM in package. So it means the package you see on the board contains actually two silicon dies. One is the system on chip itself, and the other is the RAM, which are bonded internally. So this means you don't have access to RAM directly outside. And also the package is LQFP. This whole set of things allows to have very cheap products. If you don't understand why it's electronic stuff and it's not the goal of this talk, I will be talking about software support. So a system on chip needs some software support because every system on chip is different from another. It's not an x86 motherboard, which is standardized. So you need what is usually called a board support package, BSP, or software development kit, SDK. And the kind of ideal BSP that I really would love to receive for any system on chip, and that happens with some, is I would like to have a mainline kernel, so kernel.org and get the kernel, a mainline U-boot or bare box to get the upstream version from that, with support for at least the peripherals that can be involved in booting, and good, well-written hardware documentation, because at some point you need to understand the hardware. The reason I would like to receive this is I have a kernel that has a very good quality, it's peer-tested, it's peer-reviewed, it's many testing infrastructure, so the code quality is very good, and especially you get support basically for any amount of time you want for the future, so it's well supported and you have bug fixes and so on. And also, using this component, especially U-boot, means you can reuse the booting and firmware upgrade mechanism from other devices you've already made. So you reuse the same components. It's less work to make a new product, of course. Unfortunately, this is not what I received. So this is the start of my quest, and the main steps that I will talk about you are documentation, the Linux kernel, the tool chain, booting, the tools, and customer support. So documentation, as I said, I really would like to have good documentation. On the official website, you can find an 8-page datasheet, which is basically a list of features, a very detailed list of features, and that's it. So you don't get anything else on the public website. But if you're a customer, it's very different. You receive a lot of stuff, but it's all under NDA. So I cannot tell anything about that. But luckily, there is a third way to get some material without being a customer with an NDA. That is, you can buy affordable evaluation kit, development kit, which is available from online Chinese stores. It's a pretty nice board. So you can get not only the hardware, but also a DVD-ROM with basically a subset of the material that is given to customers. Especially there is this manual, the design guide, which is basically the documentation for each peripheral that's inside the system on chip. So with that, you have a list of registers, a list of fields inside register with at least a name for each of them. For most of them, you also have a description of the device and a description of the fields. So this is the very basic thing you can work on when you need to implement or tweak or adapt a device driver, basically. Okay, the quality of documentation is, well, it's good enough if you're pretty used to reading this kind of document and you have an idea of how system on chips work generally. So you already kind of know where the pieces are and you can fill in what is not completely documented or properly documented. So it's just, it's okay, it's enough. Okay, so coming to software, the first big piece is the Linux kernel, of course, which has to support your peripherals. So basically it has to have device drivers for each of your peripherals. So the Linux kernel that is provided is actually derived from Linux kernel 26.35.4, which is being released in 2010. So it's very old, at least compared to the evolution of software, it's a lot of time. 2635.4 is not even the latest release in the stable branch for 2635. Basically, in the difference between .4 and .14, you are missing 11 months of bug fixes. It's more than 1,000 commits, and so just in case one of these bugs will hit you, it's better to merge in the changes from the .14 release, which luckily is very easy because it has minimal conflicts that you can solve. Unfortunately, the difference with the mainline kernel is huge. It's uncountable. There's a pile of new features, pile of improvements, not to mention bug fixes, especially security bugs. There are bugs and security bugs in every kernel, but if you upgrade it, you can stay on the safe side. If you don't, well, every old kernel has bugs and they are exploited in the wild, so you are at risk, at least if your device is connected to the internet. Also, you don't have device 3, so this means you have the board file mess, which is, okay, it works, but it's a bit annoying to work with. The additions to the kernel are provided by the vendor as a set of touch files. So there are huge files. There is no atomic commit or something like that. The first one is 3.6 megabytes. So it's a lot of stuff. You just pull them in and hope it works. So you cannot see exactly why this thing has been done and the reason, the details, and so on. So the amount of changes is 170,000 lines, which perhaps is a reasonable amount for a new system on chip. But this kernel has several issues besides how it's provided. Some serious issues are, well, mainly in 3 categories: bugs, missing features, and code quality. So here is just a few examples of the bugs that I encountered. One is when you try to set up audio. So the first thing I did when I want to test the microphone, the audio capture, is also record myfile.wav, and I got a kernel crash. That's because when you don't specify a channel, on the default channel there is a null pointed reference. So, well, that was very quick to fix, but it's definitely annoying. The situation was a bit worse with the H.264 codec. The decoder, for example, it works with sample stream, so a sample file that has been perfectly encoded. But if there are errors in the file, or more likely, if you're streaming from the network, it's absolutely normal that you have packet loss. So if there are packet loss, the stream is not perfect, and in that case, you have lots of crashes because of null pointer references. So either you check everything in user space before feeding it to the driver, or you fix it into the driver to avoid the null pointer references. Okay, next kind of annoyance in the kernel is it's not complete. So, for example, GPIO, it's a very basic feature of any system on chip. So they are implemented with basic functionality, but you don't have interrupt support, for example. So if you want your software to do something when a button is pressed, you have either to poll it continuously or to implement interrupt handling on your own. Power management is another issue. Actually, it's implemented in two different ways. One is with a proprietary API and one with the Linux standard API, but none of them really work. Especially with the standard API, it's incomplete and it doesn't really work. So if you need power management, you have to fill in the gaps and make it working properly. Yeah. Let's have a look at code quality. Code quality for a package theoretically might be something that you don't care about if you just download it, build it, use it, and it worked perfectly. So theoretically, you don't care about what it's inside. But in the practice, you need it in this case because you have missing feature, you have bugs, so you have to look inside the code. And if the code is well written, well, you can quite easily make your way through the code and understand what it does and find the bug. But in this case, I'm afraid it is not what happens. The code quality is generally very bad. Well, very trivial matrix, there are more than 500 lines added that start with hash if 0. So this is probably not the best way to remove code that doesn't work or something, or test work. So, but let's view a couple examples which are more specific. One is about the driver model. Since 2.6, Linux has a very rich and effective device driver model, so you can basically mix and match every peripheral with each other as far as the hardware allows you to do it. So it's very modular. But unfortunately, this is not what happens in some of these drivers. For example, this is the frame buffer driver. The frame buffer driver has this code snippet. So basically what it does is, if in kconfig you enable this display, then include this .c file. And if you enable this other display, then include this other .c file, and so on for several other display modules. So this is because basically there is no display driver. It's the frame buffer that does also the display driver, and so some of the frame buffer functions are actually implemented in the other .c file, which is which differentiates from one display to another. This means, for example, you cannot reuse a standard display driver with this frame buffer. So it's not modular. It somewhat looks like firmware, some firmware design that doesn't have the need to have a flexible device driver model. Another example of code quality is with the H.264 codec memory allocation. So as it handles video, it's quite normal that a H.264 codec needs to have pretty large amounts of memory. It needs them contiguous. So actually, it's not trivial maybe to allocate contiguous amounts of memory, but in this case this is done this way. So in the 264 codec code, there is this function which is get AVC buffer size, which refers the number of bytes that it needs for the continuous buffer. So you just ask it, and it says, 2.5 megabytes. Okay, this is not a constant. This is not a defined. This is a variable. It's uppercase, but it's just a variable. So it's not a constant. Yeah. Well, okay, not code is non-compliant. So this function gets, what is it? This function here gets exported, and it's called by the MNC, sorry, by the MNU code. So in the memory management, there is this reserve node 0 function, which is called during pretty early kernel setup. So it's what it does is call get ABC buffer size, which is this one, to know how much it needs to allocate. So this means that if we apply this model to all the kernel, MNU.C must know about every single driver that needs more than a few kilobytes of memory. And so it's definitely not scalable. And also it has a very practical implication. Since this code here is in early boot, it cannot be built as a module. So this means the whole driver cannot be built as a module, because otherwise this function would not be available at boot time. So the whole driver must be in kernel. And if you have a bug in the driver, and as I said, we have, you have to upgrade the whole kernel to upgrade the driver. So modular compilation is not possible anymore. All right, so this was an overview of the kernel code quality, and this is how, somewhat how I handle it. Approximately, I do this thing. So in my Git repository, starting from 2.6.35.14, so I don't care about .4. I want the bug fixes. I apply the patches, fixing the few conflicts on a branch where I have vendor drops. So this is the pristine copy I get from the vendor, but it's Git version, so I can do git diff and git rep and whatever. Then I have a second branch that where I apply fixes to the kernel, and I merge in the new patches as soon as they are available. And then I have a third branch where I do my development, where I merge in stuff from the fixes branches. So I can, at any time, I can, let's say, have the pristine copy from the vendor, something, the vendor kernel that builds, and my own kernel. This is one possibility to handle it. Okay, let's move to the next step, which is the toolchain. So of course you need a toolchain, but it's less obvious why the vendor provides a toolchain. So they provide a toolchain in the BSP, and it's based on very old components, just like the kernel. So basically GCC and UClibc from 2007. So there is no C++11 support. They are not at the latest bug fix release. And they also supply a few other libraries picked with some criteria. But this toolchain is so old that you basically cannot build several modern software. So basically, your design, your algorithm to pick a toolchain, at least the one that I follow, is first don't use the provided toolchain. It's too old, it's not usable. So, okay, you could use a pre-built toolchain, as many people do with embedded systems, so it's easy, you don't have to build it, you don't have build time, it's easy to use, it's ready. Okay, but since you have kernel 2.6.35, you need a toolchain that has been built with kernel no later than that, because otherwise you might have something not working. So probably the toolchain is itself quite old. Well, actually, in some cases, I do use pre-built toolchains with more modern kernel headers. To some extent, they work. So it's a risk, but you might want to try. Probably the best idea is to build your own toolchain. It's not even that difficult if you use the proper tools, at least. So there are many. There is CrossToolNG, which is very powerful and flexible. But if you want something more simple, your build system probably does one. Buildroot on embedded and others can build a toolchain. So you can tell it, build one with kernel headers 2.6.35 and a quite modern GCC. Maybe a very modern GCC and a very modern C library will not really work very well, but if you stick to like GCC 4.8 or similar, it's probably going to work well. That's okay. So next big topic is booting. Booting in embedded system is very crucial, very critical, because it's different from one machine to another because of hardware restrictions, of software needs. Software upgrades need to somewhat interact with booting, so it's a very relevant matter. It's very important to get it right. And so in the BSP, there is no bootloader, at least no standard open source bootloaders. No U-boot, no Barbox, no nothing that you probably know about. There are some proprietary bootloaders. You have the sources, but they are not open source, and they are tailored to the specific machine. Okay, so reusing components is not an option in case you have an existing board and you want to reuse the same scheme. Well, at least it's not straightforward. So let's talk about booting in detail. And this is, above you can see a quite standard booting process. There is no standard booting process, but this is one that is among the normal ones, let's say. I'll take as an example NAND flash. So the hardware itself, the system on chip, as most system on chips do, has a boot ROM inside, and so it will execute that code internally, and that is something you cannot change. And what it does is load a small firmware into internal RAM. It also is small because RAM has not been initialized yet. The 64 megabytes of RAM are not initialized because it's on package, but it's something that the system on chip die does not know about, so it's not initialized yet. This small piece of code is small, so it's usually non-interactive. It does only one thing, that is initialize the main RAM, so you have plenty of space, and then load the main loader, the main bootloader from the memory itself. U-boot is the most widely used, and it's loaded into DDR and then run. So U-boot, according to its environment variable and boot scripts, mounts in this example, mounts the UBIFS root file system, loads a kernel from there into RAM and boots it. And then the kernel will use the root file system itself. So this is one of the standard possibilities. The one you can do that is done with the standard, with the bootloaders provided with this chip, is actually this one below. So the first part looks pretty similar, and it is. So you have a first order, this is called NAND loader. It's just an SPL. So he initializes external memory and fetches something from the flash into there. The second piece that gets loaded is called NVT loader. But it's very different from U-boot or anything else. So what it does, the normal booting follow the arrow going down. It mounts a FAT partition on NAND flash, and it loads from there a file which is called conproc.bin, but it's actually a Linux init with an appended init from FS. That's it. It loads that and boots it. And in the init from FS, the init script does look in the FAT partition, mount the FAT partition, and look there for a shell script to start. That shell script can, of course, access FAT and anything else, other files, and do anything. But there is another possibility. If you press a button during boot, then the NVT loader will follow this other path and just expose the FAT partition as USB mass storage devices. So this means you can connect it to a PC and look the files in the FAT partition. This booting scheme has an interesting advantage. So it allows to very easily deploy demos. So the vendor provides some demos. These are a conproc.bin file, a script, and maybe something else. So you just press the button during boot, mount mass storage on PC, copy the files that have been provided by the vendor as a demo, and there you are, reboot, and the demo runs. So it's very easy to test. There is, for example, a demo to test the H.264 video playing, another for testing audio, for testing Ethernet, and so on. It's very easy to deploy them. Also for hardware designers, which maybe don't use Linux, they use Windows, so they can deploy them very easily. Okay, but it also has disadvantages. One is it uses FAT. FAT is absolutely unreliable, especially on power loss, and it cannot contain a root file system at all. It doesn't have permission, users, symlinks, and so on. So it's not an option for your root file system. Also, FAT is on top of NAND, which is unreliable, and there is a flash translation layer that allows to have a somewhat reliable virtual partition to put Fanta on. This works, but it's a binary module. So if there's a bug in there, you can wait for vendor to fix it, or otherwise you're on your own. And also, this scheme, there's no provision for redundancy at all. So if any of this component is on is corrupted, or maybe during upgrade you break it, the device will not boot anymore. So you have to connect it to a PC and refresh it. But if you're on the field, in the world, it doesn't work. Other issues are well, more related to Linux stuff. One is the root file system in this scheme is an initramfs. Initramfs is cool, it's fantastic, but it's in RAM. So changes are, you can change the files, but the changes are volatile unless you save them somewhere else. It also has a limited size, and everything it contains is stored in RAM. Even things that you don't use sits in RAM for the whole existence of the initramfs. Okay, you could store persistent changes in the FAT partition, but of course you run into the issues that FAT has. Also, in this component, nobody passes a command line to the kernel. So if you want to change how the kernel boots any parameter, you cannot do that. This is, for example, this is an issue during development. If you want to mount your root file system over an FS, you have to change the kernel command line, and you cannot do that because you cannot, well, you can, but you have to rebuild your kernel, refresh your kernel, and then boot. And when you want to switch to non-fresh booting, you have to do it again. So it's very uncomfortable. Okay, and finally, these loaders cannot load the kernel via TFTP, which is another very handy thing to do when you are doing development. If you're developing a kernel, you want to test a feature that is not in a module, then you could just load it via TFTP and test it very, very quickly. But it's something that you cannot do in this case. Okay, so I started looking for alternative booting options that solve at least most of these issues. And so here are the steps that I did, the step-by-step guide. So first step is, okay, keep the system as it is, but add a squashfs root file system. So you have a file system that can be as large as you want, but reasonably large as you want. And it's efficient, it doesn't keep everything in RAM. Okay, so it's a little step ahead, but it has drawbacks. It's read-only, and also it's not yet possible to do atomic upgrades on that because it's on FAT, and so on. So it's not really a good improvement. Next step, okay. In the Linux world, and once we have a Linux kernel running, we have plenty of options. We have UBI and UBIFS, which are very good for non-flash. They are efficient, scalable, I mean, quite scalable, and they work very well. They handle bad sectors, and it's a proper Unix file system. So one idea is this one. You just restrict the FAT partition to be as small as enough to contain the kernel, and then you tweak the initramfs to not mount, not look for a shell script, but to mount your UBIFS root file system. So in that case, you have everything that is, I think, most of the things that are relevant for your product inside this, where they are safe and you can do atomic upgrades and so on. On the other side, you lose USB mass storage upgradability. So at least you can still use USB mass storage to upgrade, but only basically the kernel and the initramfs. For the UBI stuff, you have to do it with other means. So basically what we did is the FAT area is now atrophied to the minimum size, and NVT loader does not do its specific feature, which is upgrading via USB cable for demos. So we lost most of the advantages of this scheme, so let's get rid of the scheme at all as far as possible. So remove the FAT partition, remove NVT loader. It is possible because NAND loader can just load a Linux image file, not a Z image, but an image file at address 0 and boot from it. So you can have your kernel Linux image processing from FS directly in NAND, and it will be loaded, and it will mount your UBIFS. So you have less components on it, so less bugs, less boot time, and so on. Okay, so the flip side is your kernel is on bare NAND, so it's not in a safe place, and so you need to at least provide space for 2 copies of the kernel in case one of them fails, but then the loader does not directly handle redundancy, so you could tweak that. Or you could use some different scheme, maybe using kexec to load another kernel from a safe area in UBI and so on. So there are different variations, several variations you can do, but you can elaborate on that. But actually, the final step would be to port your boot to this system on chip. This would be probably the best because in this case, well, you can keep the SPL. It's quite okay, except it's not redundant, but in this scheme you basically have all the possibilities that you know in other embedded systems. So if you have other boards using U-boot, you can just use the same scheme, do the same things, and save a lot of time while having a lot more features. Unfortunately, if you ask your boss to do this activity, to plan this activity, you have to keep into account it will affect time to market. And unless you're used to this kind of activity, it's a bit difficult to understand how much time it will take. Okay, so I'm afraid I didn't do this, so I don't have U-boot for this chip to present. Okay, next topic is about tools. Actually, in the ideal BSP that I presented at the beginning, there are no tools, if you noticed. That's because it would be great if you could just work with standard tools, open source stuff, without having to rely on anything that is vendor specific. Sorry. But actually, several system-on-chip vendors tend to have a boot ROM that speaks a proprietary protocol, so you need a specific tool to interact with the chip when there is no firmware, no software, nothing on your flash. So at least for development and for production, probably, you need to interact with the chip without anything, any piece of software stored in the memories. So you need to store the first piece of software there. And it's also useful for development. So basically, you need some tools. And so what you get is this one, which is you get a tool that allows basically to connect via USB to the system on chip, interacts with the boot ROM, and it can flash several types of memory, NAND, NOR. It can also put your stuff in RAM and execute directly. So it's pretty flexible, and USB is very handy. So it's quite good. At least the design is quite good. The software itself is, it works, but it's for Windows only. So you need a Windows machine in addition to your Linux machine just for this tool. And it's completely proprietary. There are no sources, so you cannot modify, extend it, port it to Linux or anything. And it's a GUI software, so you cannot put it in your script to automate any goal, any task that has to do further steps. Finally, the protocol between the boot ROM and the PC is not documented. So this doesn't allow to write your own tool. Basically, you're locked to this tool unless you want to reverse engineer the protocol or the tool itself. Another peculiarity of this tool is what it does is it maintains a sort of partition table in NAND flash. It's unusual because there are partition tables on hard drives and similar, so SD cards and USB drives, but in NAND flash there is no standard for having partition tables. So it might be a good idea because it actually allows to organize data and the device describe itself. Okay, so this is done, but without using any standard, so it's a proprietary scheme that is quite tailored to how the other tools work. So basically, since the tool enforces this partitioning scheme, you cannot get rid of the scheme itself. It doesn't hurt very much, but you just have to know it. So basically, this is where it stores close to the NAND loader the list of where you can find the next firmware and at which address in memory you have to load it. Okay, so another topic here is customer support. So if you had a perfect SoC with a perfect BSP, you don't need customer support, but I don't think this is realistic even in the best cases. So you need some customer support at some times. And generally speaking, with system on chips and vendors in general, there are several issues that can happen with customer support that make it more or less effective. But what matters if you have standard mainline code, you don't have to stick to the vendor. You can have support from the community, from a plethora of vendors, of commercial support providers, and so on. So you can have many possibilities. While if you have, such as in this case, you have the sources, but it's not in the public, and it's a very old kernel, almost nobody will support you except the vendor and yourself. And if you don't even have the sources, such as for the tools or for the hardware itself, it's only the vendor, so you have to rely on them. And something that can go wrong in customer support is, well, the engineer in the vendor company who knows the answer is not directly reachable. There are salesmen, customer support department, and so on that filter. So it might be difficult to reach the person who knows the answer. Also, responsiveness is an issue. Some are responsive, some are not. And you might have times and issues if you are in Europe and customer support is in the USA or in China. You will have a one-day delay at each iteration. So actually, in my case, for this chip, customer support is quite responsive, so you get a reply the next day. But sometimes they solve the issue, sometimes they not. So this is a bad example. So I wrote an email saying the proprietary tool doesn't work on my PC, and the reply was, it works on mine. See the screenshot. Okay, so next day, next email, okay, on mine it doesn't work. Can I have some logs from the software so I can send them to you and can debug it? And the reply was, I'm sorry, adding logging would not be practical. So I don't know exactly what it means, but basically I had to solve the issue on my own. In other cases, they solved the issue, so it's like a 50-50 situation. Okay, so let's draw some conclusions. The result, the final result on the product to be developed is the product now works, but the overall quality is less than it would have been with another system on chip with good support. So it has issues that shouldn't be there. Also, it doesn't exploit completely well the hardware, and so the hardware would allow to do much better, but the software is an obstacle. We spent a lot of time, as you might have imagined, in supporting ourselves, fixing bugs, filling in the gaps, and in reinvent the booting mechanism, as I showed you. So a lot of time spent is a cost, and it has impact on time to market. So it's bad for basically for everybody. And so I started wondering what could be done to improve the situation. And okay, what can I do to improve the situation is, well, as an embedded Linux engineer, what I can do, and I should do is try to assess any potential problem, any obstacle as early as possible. So especially with respect to booting and to hardware support, the drivers and so on, test them as soon as possible, try to understand any possible issue as soon as possible. So if it's soon enough, you can influence the choice of one component or another. Also, well, as a hobbyist or as hacker, there is something you can do, like if you want to buy a board, buy one with good support. So, okay, but I'm afraid as a single hobbyist, it will not move the market with your by choice, unless you really build something that is so viral that thousands of people will want to do it. But okay, congratulations in that case. Okay, so another thing you could do, and that would be very much appreciated, is roll your sleeves and start improving support and mainline it. So it happened with other system on chips, like the All-Winner family, for example, and the result is great. So, but I'm afraid this is not work for a couple of days, absolutely. So who is able to really change the thing is, of course, the vendor, because it's their choice to provide a good or a bad BSP. So this is a basic equation. Good BSP means happy engineer, so the happy engineer will make good products, and good products will sell more. This is somewhat a generic rule that somewhat applies, but it is generally not very well perceived at some high-level decision points. So let's go into some more practical details. So first thing, don't reinvent the wheel. It will take less time to port U-boot to your device than to implement your own bootloader. And when you're done with that, you will get a lot more features. And after it's there, and if you mainline it, people will improve it, and basically it's for free for you. People will fix your bugs in the kernel, will add features without even you to have to move one finger. Okay, so so try to push code to mainline is definitely the best thing for long-term software support for your device. So if you do that, well, it's expensive. It takes time, and it takes some skilled people, but in the long term, it's rewarding. The products that are built on your chip will be better. And finally, leverage the community. So if it's upstream, you're already doing that, but also software support. Let your engineers reply to questions on public mailing lists, on IRC, on public channels. So everybody benefits. If I look for a question, it's probably already been answered somewhere else. I don't need to wait for the next day, and other people can improve the answer. And your engineers will not have to reply to the same question to 10 different customers. And well, also making cheap boards that are hacker maker friendly, like Raspberry Pi and Bigger Bomb Black and so on. They sell a lot of chips, and they allow a system on chip to be easier to use for real products that are based on custom hardware. I'm afraid in this case it will be pretty hard, because the chip is really slow compared to any hacker-friendly board that you can find around. So it will be very difficult. But if you have even a little more CPU power or some specific features that other chips do not have, this could really be a way to allow people to start hacking on your software and contributing to it, making it a little better. So, okay, I hope these will happen to some vendors at some point. It happened in the past to some vendors, so there is hope. Okay, that's all. Yes, question? Okay, I think the man was first.
Do you have an opinion which vendor is best if you look at the previous slide?
So the question is, do you have an opinion about which vendor is best? Well, I don't want to advertise, and I definitely don't have a complete view of the market, but basically just go to kernel.org, download the latest kernel, and check which chips are supported.
I was thinking more of the booting process.
About the booting process, download the U-boot sources and check that. Yeah, but anyway, for the chips I have seen in the past, most vendors provide U-boot. Maybe it's an old U-boot, it's not in mainline, but it's still U-boot, so it's still a standard component. So a 5 years old U-boot already does a lot of things, and so it's better than nothing. Question?
My question would be, why would you choose such a chip with such a crappy software support? It's not 2007 anymore. We didn't have any choice.
Yeah, well, the question is, why did you choose this one and not another one? Because software is not the only component. There is also hardware and cost. And okay, so I think, yeah, it was cheap. Yeah. Okay. Any other question? Yeah.
So my question is, isn't a problem of vendors actually to put their technical debt into mainline, so you don't need to do these awful things with software, so you everything get from, for example, from kernels, was adaptation?
So the question is, it's a problem for the vendors to...
Yeah, it's a problem of vendors to put everything to mainline, kernel and stuff and everything, and then you don't need, to do many things to set up your board.
Okay, I agree with you. Somewhat, he said it's a problem of vendors mainlining their code, their software support. Actually, it is not mandatory, of course, so they can choose, and it takes time to do it. It takes money because people have to work on that. It takes more time than developing bad software. Good software is more expensive than bad software, so they can just send the salesman and says, there is Linux, it's real, there is Linux, but it's a little bit more different to understand the code quality. So yeah, for some vendors do take like the responsibility of doing mainlining and the advantages. Some others, they don't do the investment. That's what happens, sorry.
Yeah, so, and the second question, why should we pay for vendors who are not supporting mainline?
Why there are vendors that are not supporting mainline? Well, I think they are a bit short-sighted, but okay, you should ask them, I'm sorry. Yeah?
Did you find a relationship between the quality of the BSP and the quality of the hardware itself? How many bugs in the SoC and the dev board did you try?
Okay, so question is, did you find any relationship between the quality of software and the quality of hardware? So bugs in the hardware and so on. I'm not a hardware designer, but I work with the hardware designer. So the hardware generally works quite well. We have a couple of problems, but overall nothing really big. So no, the hardware does not show big problems. So it's very unrelated. Of course, the people who do the hardware and the people who do the software are very different, and maybe also their bosses, so the approach is different. Yeah?
Have you told your marketing contact or whoever you're in contact with shipment?
I'm sorry, I cannot hear you.
Have you told your marketing contact in the chip manufacturer all the stuff you presented here in your talk?
So if I understand correctly, is there some marketing material?
No, have you
You
told
get feedback
your
through the
marketing,
of the
the
company.
guys where you bought the chip or the stuff you presented here, what you don't like?
Okay, if I told them the issues I had, not much really. I don't have access to marketing and high-level people. I have access to engineers who provide support, but no, I didn't. I might send a link to the slides maybe. Yeah.
So this is sort of related. If you buy a Windows laptop, it generally has this, good for Windows version X sticker on it. could some sort of marketing effort, you know, sort of guaranteed mainline Linux and some logo, could that start to move the market? Because, you know, that's something you can point at to a marketing guy to say, well, your competitor has guaranteed mainline Linux here.
Yeah. That's
Why
very
don't you?
interesting. Yeah.
So, do you think that could make a difference?
Well, that's very interesting. Probably a good idea. So the question is, do you think that something could change if we had some sort of logo, like it's Linux mainline compliant or something like that, like the works with Windows stuff? Well, probably it could improve situation. So if there is something like standardized by maybe Linux Foundation or something, so you can put a logo saying this is in mainline, so good quality, or there are the sources, so some not so good quality. Yes, it might be good. I cannot say if it would move by decision, but it would be a good starting point, definitely. Thanks. Okay, one more question. No more question. Okay, so thank you. No question. Thank you.